Good afternoon. Today our report is robust multi-layer Kevlar Aerogel for high-performance sensors, and we're from Huazhong University of Science and Technology. Our report including 4 parts: background introduction, experimental methods, characterization and property tests, and the potential application. Let's start with introduction. Sensor technology are widely used in industry and the medical field. And now sensors, we divide sensor into 2 types. The first type is rigid-based, such as silicon-based sensors, and the second is flexible sensors based on polymer base. Compared to silicon-based sensors, flexible sensors have a wider potential application due to its portable, light-weighted, and shape stability. And as you know, sensors always have complex function and integrated structure. Different from silicon-based sensors with mature integrated circle fabrication techniques, flexible sensor requires a more integral structure by combining different functions, including signal transmitting, electromagnetic wave insulation, and dielectric properties together. And flexible sensors requires a surface consistence with the base material, such as skin or bearing, to better obtain signals from the base, such as temperature, vibration. So the thickness of the flexible sensors also need to be valued. So we believe aerogel are a great candidate for fabricating flexible sensors. With a great development of material science, aerogel have attracted people's attention and has been widely used for its unique properties, such as low density, high porosity, and large specific area. Therefore, they have been widely used in aerospace, building material, and chemical engineering. Traditional aerogel often refers to bulk aerogel with certain thickness, but their bloated size may limit their applications. Aerogel film exhibit the same structural characteristic with more compact size, so they are great candidates for fabricating flexible sensors. So, as mentioned above, a key technique is to integrate aerogel film with different functions together to a united one. So traditional fabrication method for multifunctional aerogel always focus on integral structure and function, and they focus on intrinsic multifunctional property of the nanofiller. But however, it is hard to combine different functions together as desired. So herein, we propose a new fabrication strategy for the preparation of the flexible sensor with multi-layer structure by integrating different functions to a single nanocomposites. Then let's introduce our experimental. We use Kevlar textile as a base material for the aerogel, and we use an alkaline-assisted method to broken the hydrogen bonding in a strong polar solvent in DMSO. Then we thermally or electrically functionalize the aerogel film by adding functional nanofillers such as boron nitride or carbon nanotube into the dispersion, and we use blade coating method on the glass bases and immerse them into water for solvent exchange to remove the residual solvent. Finally, we freeze drying them to obtain a single layer aerogel film. And after the last step, we coat a thin layer of aramid dispersion on the surface of the aerogel film, and we piling them together and load a pressure on top of it to help the dispersion penetrating into the meso and micropores. Then we repeat the process for solvent exchange and drying. So next, let's introduce our characterization and property test. First, this is a SEM image of the morphology of the Kevlar textile before and after the fabrication process. The nanofiber was dispersed into a solvent and then combined again in the water. Multiple materials can be added to the dispersion as desired to thermally or electrically functionalize the aerogel film, and we choose boron nitride as an example. It is clearly that the boron nitride was found to inserted on the surface of the aerogel film. And then we're discovering the fabrication mechanism by observing the cross-sectional image. The sample was fabricated with a boron nitride functionalized layer as structural layer and the pure aramid dispersion as adhesive layer. which the structure layer is marked in the red box, and the green box means two connection layer. It is all we can find that the different structural layer was connected by the appearance of the connection layer, which was fabricated by the solidification of the aramid dispersion. But we can find that in the green box there is still the appearance of the boron element. The proper explanation will be the dispersion, the dispersion dissolve part of the neighbor layer, and they reprotonate again in the water to form a connectional layer to connect each structural layer. And we carried out mechanical tests. The multi-layer aerogel shows a huge mechanical property improvement, and the property improved 2700 and 116% of strain and stress for respectively. Let's talk about the potential application of our techniques. We want to use it to fabricate a capacitive pressure sensor with density gradient structure, since different density layers can exhibit different strain response under different pressure input when they're combined together. So we believe they might be able to have a wide pressure response. And this is another application. We can use it to fabricate flexible for gas sensors and other sensors. We can integrate the sensitive layer, the heating layer, dielectric layer, and the flexible circuit based on PI substrate. We can combine them together to form a complete structure of the flexible sensor. Okay, that's all. Thanks for listening.